for this lecture, I think I will just speak. It's okay. Okay. We've actually come to the final part of the assembly language series. We have 3 lectures. The first lecture is basically an introduction about what is assembly language. Why we need assembly language is because of the optimization. Okay, so when you write in C, I've actually shared a lot of times. C is basically much nearer to our human language. It's presented much nearer to a human language, and therefore, you know, it doesn't optimize on the usage of hardware. Let's say, for example, in C programming, you don't see much of a hardware in your C programming. Okay, although you might see some registers, say for example P out and all this kind of thing. Other than that, you don't see a lot of hardware written in the codes. You cannot visualize. Okay, so I just like to talk about a bit about lab 3, lab 4, and lab 5. I think it's more to the assembly part. Okay. I think most of the labs are handled by Dr. Filbert. Me myself, I'm more to the lectures and the tutorials, but off and on I will come and assist if you guys have any, because the labs is in a way connected to the lectures and tutorials as well. Okay, so I think I just want to comment. All right, the template that's given to you for the blinking LEDs for the labs. You deal with a few of the you deal with a few of the registers. P out, you know, P in. P in is basically for checking. I think you've covered that in your lab 1 and lab 2 as well, the C programming part. Okay, so all the labs, you know, is fundamentally it's all about just these few registers. Okay, the PX out, whatever value that you put in, okay, you will blink the LED. And I know a lot of you guys are copying the past year. You know, you get a code from your senior. We purposely change a bit so that you don't copy exactly and you do the lab without understanding. Okay, in that we actually change a little bit so that you guys can actually put effort to learn. In particular, I just like to point out that whatever values that you put in, let's say for example you put in 0x001 to P1 out. Okay, so your P1 out, it's the least significant bit will be set to on. Okay, so if you put 0x00, okay, for your P1 out, what will happen is that all your LEDs connected to your P1 out will be 0. Okay, so we did a little bit of change to make sure that you guys do not copy 100% from your senior's code. Okay, but you can use it as a reference. I know a lot of you have. Okay, it will be naive for me to assume that you did all the labs all by yourself. All right. So most importantly, I like you guys to just have a little bit of understanding. Okay. I might actually some of you, I've been talking to some of you personally. Some of you text me and said, "Hey, sir, you know this code and how is it? You know what's wrong with it and all these kind of things." I've been doing so personally, but I'll see how, because there are some important topics to be covered. If I have time, I will come to your labs. Okay. So today's lecture we will discuss about macros. Okay. So you can think of macros as a form of function. Can you do your code without macros? Definitely. You guys have been doing a lot of just by using labels. Okay, you guys have been doing delay functions without label, just by using labels without application of macros. That's possible. Okay, and then for item 2, 3, and 2 and 3, it's basically it's a new concept for you. It's called relocatable source. It has nothing to do with a lot of the making the LED function and so on and so forth. It's more to the code optimization. Okay, so this item number 2 and 3, it's basically about changing models. Okay, so some of you you're very familiar with just one or two type of embedded system. Okay, so but in the case where you're dealing with, let's say for example, you're dealing with you're in a handphone company, your IAR system takes into account the let's say the ARM processor. Okay, and a lot of times you design something, camera or whatever, to work with the ARM system. Suddenly, there's a new model come. Let's say, for example, ARM 7. You're currently using ARM 7, and you're assigned to design a new model. Okay, using ARM 8. So a little bit of the memory allocation is a bit different. That's where you need to use relocatable files, relocatable sources, where you save the codes and etc. Okay, so normally you use the directives org. Okay, that's very simple. You start from this 0100H or something like that. Okay, so your code will be stored in a position. Look back into lecture 2 or lecture 3. There is this file called the linker file. Okay, where you're able to find out, each of the instruction, where is it located. So it's in assembly language is very manual. You do things manually, and that's where you have an absolute control of your embedded system. Okay. So to simplify parts of the code that are repeated several times, one example that you can think of is what they call the. Before that, let me check at the. Let me check your chat room. Any? Okay, no chats. Okay, that's good. All right. So this macro, you can think of it as the blinking of the LED. One of the sections of the code that you always use is probably delay, right? And you probably have you want to vary the delay time. Okay, some of you are saying that hey, there could be this is for those who love challenges. Okay, for those who love challenges, the delay. If you what happen if you want a very long delay? Okay, so if you want a very long delay, there is a way to actually do it in a very nested way. Okay, but some of you are saying, hey sir, the counter is already maximum. It's 10 bit and so on and so forth. There's a way to do it, in terms of changing, modifying that section of the code to probably double or triple. It's called nested method. All right, but it's not really covered. You need to cover a lot of things in this introductory course. So I'm just going to tell you that there is a way by doing nested method. Okay. Now the delay is something that you can think of in fact many of the functions that are inside your MSP board, the libraries and so on and so forth, even your click tree. Okay, you know that if you take out the click tree board, if you have opportunity, I think many of you do not have opportunity to see it physically because you come into this class, you are already virtual. Okay, so you're virtual engineer. You look at the click tree board. Actually, the click tree board is not something that we buy. Okay, it's actually developed by our Bentley counterpart. And this click tree board is basically an MSP product. Okay, you can see the casing is an MSP product, which we just connect to the other parts of the board. Okay, and if you can see that there's always a blinking yellow light, that's what they call the heartbeat. Okay, so there's actually two embedded systems, one on the board to control the outputs, and the other one is basically the MSP 430 itself. So that you have two. Okay, and you always check. Okay, the board is no heartbeat. Okay, there's no blinking of the orange color light. Means to say that the onboard embedded system is actually hang or not working. Okay, so we look into this, how we can we always update our equipment. Probably if we have time, we can design from scratch, the click tree board. Okay, in terms of stability and all these kind of things. So let's say for example, if you are asked to design the click tree board from scratch, okay, using the MSP, what would you be looking at? Okay, of course you'll be looking at what is the training module for. Back in those days we have this thing called the leaf. okay, we used to have this the lift, okay, to as a part of the syllabus. What happened is that this lift becomes old and a lot of parts are actually not functioning anymore. So we actually scrap the lift from this unit, okay. But before this, there was this lift, okay, and this lift, okay, they have a lot of registers associated with this lift, okay, and we designed our click-free board to be able to work in line with this lift. It's a lift, it's a mechanical toy lift, all right. So there's a lot of registers and a lot of libraries that we actually write in assembly language. We use a lot of macros associated with all these kind of things. Okay, so macro simplified shortens the user source. Basically, it's for the user. It makes it very simple. You can actually associate macros with function. It's very easy for you to understand. Function, you've been dealing with function a lot of times. Why do you do function? It's because you want to simplify your code. Can you write something without function? Definitely yes. Okay. In a time-intensive application, the overhead in calling and returning from subroutines could be a problem. Okay, this is very true. Every time you call a function, there is an overhead time. Okay, so you spend a little bit of overhead when you are calling a function or a subroutine. Okay, but other than that, the advantage is that it makes your life much more convenient. Okay, so if you can develop an embedded system and you really want to minimize on the function, okay, you can do so without the function, because every time you call the function, there is a overhead time. Okay, you call the function, it could be 0.05 microsecond or whatever. So if you repeatedly call this function every time, you can imagine how much time is actually being spent just on the overhead. Okay, overhead means the processing time that is nothing to do with basically your LEDs or whatsoever. It doesn't contribute to the functionality of your code, but it's basically just for calling the function. Even when you're doing the for loop, if loop, and all this kind of loop, do you know that actually there is an overhead when you call a for loop or if loop, right? So there is an overhead for everything. When you're at that level of application or design, you would actually look in depth on this situation. But for this introductory course, we're just going to worry about C, assembly. As long as you know roughly how to do it, it's fine. Okay. A macros must be defined before it can be used. One of your friends actually texted me, on the delay function. I think he copied it from the book and all these kind of things, and you can see basically it starts with the macros definition, and it ends with nm. M refers to macros, so you end the macros. You start with a function call, define, and you end with the nm code. All right, it's possible to pass parameters to macros and to define local variables, especially labels, which would the assembler will differentiate in the different expansion instances. So you can pass local variables. Okay, like for example with respect to the delay function. Okay, you can pass how much time to delay, etc. and etc. Okay. So it goes like this. Okay, you have your macro name. This is the starting of the macro. Macro name, your argument, first argument, and then your second argument, and it must end with the code nm. Okay. Here, macro name is the user-defined mnemonics for the macro. You can call it anything. Okay, you can call it anything that is not reserved word. All right. So there are a couple of reserved words that you're not supposed to use. Okay. Assume that an LED is connected to P10. Okay, again, I just take this opportunity to reinforce on some of the questions that makes you very unfamiliar. P10 means port 1, pin 1, or port 1. Okay, it's P1.1 means is the second pin of port 1. Okay, so you have to understand this clearly. P16 means is the 7th pin of port 1. Okay, so you really need to look into these technicalities and this term. If you don't understand this, you can you can send me an email or you can text me. I can explain further to you. Okay. Assume that LED is connected to port 1, the first bit of port 1, and a green LED is connected to port 1 6. Okay, that means it's a 7 pin. Let us define it as bit 0 or the green LED as bit 6. Now the following macros is defined on an LED, the number of times defined by how much time. Okay, how many times you want to repeat it with speed determined by delay time. You can even define, okay, how much I want to define and how many times. So if you want to make the delay longer, you can change this times, means to say that how many times you want to run this delay. Okay, it can be a few times, okay, whatsoever. Now look at this. This is the definition of the module. Okay, you can the macro name starts with this is the macro name. Okay, and these are the arguments. Okay, you have your delay, and they always end with nm. Now a lot of you are still confused about jump not zero, jump not zero. I think you better look back into all these kind of terms. What is JC? JC is jump if carry is equals to 1 and so on and so forth. Now, I cannot be spending too much time to explain every single assembly function there is. I'll be focusing more on those that have related to the lab. But it's actually your job to actually go and look at the book and to actually understand what are these. Okay, the rare ones you have to read yourself in the book. Jump not zero means to say that if zero flag in the status register is equals to 0, reset means to say that it will actually jump to this label called counting. Okay, so you can have local variables. So times and delay time is local variable. It doesn't work outside of the main loop. Okay, so in this definition, RLED 6000 will cause the CPU to turn on and off the LED 20 times. So it will repeat 20 times. Okay, so similarly, this will give you, if you would like, the LED 10 times. Okay, so it will delay for 10 times, twice the speed. So similar with this. Okay, so you really need to spend time to understand this guy, how does it work, you know, the delay time is transferred to here, and you know how does it work, you know, why do you use register 15? You can use any other common registers, not really 15 or 12. Okay, so it's up to you. And very well could be something like this for your exam. You know, it could ask you, you know, what if I want to multiply it, you know, what if I want to blink it, you know, another how many times, and so on and so forth. How would you change this part of the code? Okay, so you insert values into this, and questions can come out in such a way. So it's basically nothing complicated, but it's basically just a function. Okay, so we've actually discovered that some time ago I told you that this MSP 430, they have this function called multiplication. Makes it very easy for you to do something, and you basically have to just key in the MPY OP2, and you have an answer in the two registers. You combine it together, you get the answer. Well, behind that function is basically a set of macros. Okay, where somebody wrote this, and you know that's why you get the answers. All right. So behind this multiplication macros, someone actually wrote it, and you can actually write it for something else. You can write it to, let's say, for example, your servo motor. We haven't actually touched on servo. I believe it's not in this unit, but servo motors, you can write a macros for servo motor. How much how's, you know, the duty cycle that you can you know. And for this reason, if let's say you were to write some macros for the servo time, definitely this would be one of it. It could be the angle, how much angle you want. Okay, and you know, it will output the correct pulse rate, okay, for the to make it spin at a certain angle. So this is an example. Think about this. What other macros that you can write to make your life simpler? All right. So it could be other things. Think in terms of whatever that you've learned so far, because complicated things like serial communication, so on and so forth, that could be some other time. But for your level, it's more to servos, motors. You can write a macros, how fast you want to run a motor, interface it with the electronic speed controller, so on and so forth. Okay. As a reminder, the basic layout for a source file consists of documentation. So every time you have this source file, for the macros and so on and so forth, make sure you have complete documentation. Documentation is something that at the moment you don't care, but when you really go out and work, that's where your performance will be defined, because you pass the code from one person to another for development. You don't do the whole thing from scratch. Okay. So the order is not necessary, as you mentioned. It might be different with exception to end directive. Also, executable file, reset, interrupt, allocation are compulsory. Okay, so these are some of the things that we will discuss at the end of the lecture. We have a section on that. Okay, talk about the reset, interrupt vectors. A lot of the interrupts. Okay, that we want to talk about. Okay. Now we've come to the second item. Basically, macros, I summarized that it's basically just a function, but it's an assembly version. Okay. The next thing we want to talk about is basically more towards code optimization. Okay. So the next slide shows comparison between an absolute file and relocatable file. So we're just going to show you this example. Now, bear in mind that some of these questions actually have come out for your exams previous years. On the relocatable file. If you're not familiar, then you can just understand it's more to theory. There's nothing to calculate, right? You have to know the difference between relocatable, what it's for, how to use it, more or less that. There's no real calculation or application on that, all right? So it's more to whether you know what is it about, right? Now, look at this. Wait, let me have. Okay, of these two, uh, this one is basically the versions on the right hand side is the version that you is called the absolute directives. Means to say that it's defined. You can see this part is defined. All right, and where the code is stored is also defined. You have your originate from 0f 800. So this is where your code will be stored. Starting from here, the offset, whatever that you have here will be converted into the equivalent. Machine language, it will be stored starting from this point. Have a look at this. This is done using the linker. Means to say that it's not defined. Okay. A very good example. One of your friend called Kwang. I think he texts in the common group, sir, why is this? There's a problem with the reset address. The error is showing that there's some problem with the reset address vector. Okay. Now, what he says is that he allocated certain interrupt registers. I'm not sure that whether this is what he entered, FFFE as the reset vector. But if he entered wrongly, different models would have maybe different models would have different reset address. Okay. Now, rather than have this, if you know your system very well, you can do this, no problem. It'll work. Okay. You save your code here, and codes could be linear. It could be segmented. The memories. Okay. We are not very sure which model you're going to use. And then you define your reset address. Now, most of the MSP products have the reset address at this point, but sometimes you might want to use different models. That's where you have the problem, and it's better to allow the linker to assign it automatically. Okay, so you can see the difference is this part. This one you manually assign where should the code be saved. This part you pass it to the linker, let the linker do the job. Right now, easier said than done. All right, the whole philosophy of this absolute directive and this using relocatable source file, it's very easily said than done. Okay, we just say that, okay, we want to do it automatically. How does the system actually works? And it makes it takes advantage of several mechanisms that are available in your board. Okay, in relocatable file, we use segment directives to define our work memory. For example, this one. Okay, sorry. Okay. So if you're using absolute codes, you define it. In relocatable codes, we use segment directives to define our work memory. So you don't dictate it. You let the segment directives to do the job. Absolute codes have the disadvantage that a program written for one model may not be suitable for another model because of the different memory map. Okay, we know that some memories, the accessible memories, are not linear. You come to a certain memories, these are memories that are reserved for certain reasons, okay, that you should not touch. Relocatable codes help solve this problem by leaving the storage work to the linker, so it automatically define. Why is the system so smart? Okay, in relocatable codes, the object file is organized by relocatable sections. So you divide it into sections, managed with the use of segment directives. A section is a block of code or data that occupies a contiguous space in the memory map. So we know that, okay, certain of the codes, let's say for example, part of the code must be, okay, certain segment of the code must be one piece. It must be stored, saved in a continuous form. We know that this could be one section and another could be another section. Okay, so we can divide it into sections. Okay, relocatable sections. So these are sections where you write the code and the linker automatically compile. Okay, this section must be one piece. Another section could be one piece. Okay, probably the function could be in another section. Okay, so the most basic part where it needs to be continuous is basically called a section. Okay, each one has an associated section program. Also called section location counter, which is initially set to 0. So this section starts with this address, and the rest is basically just offset from there. The section location counter function within the relocatable section only, signing and offset. So easily said than done. We want to have an automatic system. How is it done? So you make use of this system called section location counter. You have a section location counter for each part of the sections. Okay, the actual physical address allocated is done by the linker. So this is how the mechanism works. The linker assigns the physical address. All sections are independently relocatable, which allows the user a more efficient use of memory. Like what I mentioned in the previous, I think it's the memory section of the lecture. You check whether it's a 3 or 4, I'm not so sure. Each of this section, each of this memory could be a linear memory, or they could be a non-linear memory. It means to say that you cannot access every part of the memory linearly. Okay, there are certain parts of the memory that are reserved for certain purpose. It depends on, but ideally it should be linear. All right. Now your IDE, the IR starts allocating section with directive rsec followed by the type and name of the section. So you can basically put, okay, this is one section that I've assigned, the one rsec that I've assigned, and this is another rsec that I've assigned. So it helps you to automatically, the section linker will help you to do the job. In MSP model, some address of the section have names attached to it. An important one is reset. Okay, so this is reset. It's basically this name is hardwired to the reset address. Okay. Types of section include CStack, code, data, etc. R stack and C stack creates a stack on top of the RAM. So this is how you define. Okay, I want this part to be a relocatable segment. In the example, we initialize a speed. Okay, so this is basically you can define an R stack and C stack. Okay, so the C stack is maybe, okay, I want a stack of memory, but I let the linker basically to define where should this stack of memory be. Okay, so we can see the action of the section program. It keeps track of the offset address within. Okay, so basically this is how it works. Okay, creates a stack. Okay, creates a section. Okay, and then allocates the reset, allocates. So basically, you know, even the reset address, okay, can be dynamically defined. Okay, so you need to have define it as a double word. Okay, reset. Okay, so you can basically have one code and just do like this. And it will work for another model. All right. Now, in addition to the assembly time constant, we also have variables and data. So you can basically have apart from constants, you can have labels associated with data. Let's say, for example, an array. Okay, an array. You come across some programs that you need an array. So basically, this is how you do it. Okay, you have a label, and you have the type of data, and you can call it, you know, what is the data itself, 0x something, 0x something, you know. So you have to use the definition. Okay, this is how you use the definition, whether it's a double word or double long, or is a double byte or whatsoever. Have a look at this. All right. So you want to assign the reset address. You define it as, you know, double word, because it could be let's say, for example, it's 0xFFFEE or something like that. So it's a double word. All right. If the constant is to be maintained fixed and kept when the system is de-energized, is preferably stored in, you can have a choice to store in a RAM or in a ROM. Okay, so if you want to have it permanently stored in the ROM, you can actually choose to do it. More examples of this is actually in the book. How do you make it to store in the RAM? How do you make it store in the ROM? So basically, this is actually storing variables. Okay, I have a, let's say, for example, you have programs. Okay, let's say, for example, you're designing let's say a machine learning model called KNN. Okay, K nearest neighbor. When you deal with K nearest neighbor, you need to store basically the training sets in the machine learning model itself. So you can design it, you know, using this method where this data could be the training sets. All right. So this is one example of how you make use of storing variables in your embedded system. Keep in mind that the label points only to the address for the first byte. Okay, you can assign it. Okay, so even though the user can define a floating number with directives, you know, okay, this is basically nothing much. Okay. So this is an example, okay, of how you do it. Okay, you can equate a delay, okay, using this method. Okay, so delay, you know, TW 5,000, because it's a double word. You convert this into binary line, you know that it's a double word. So the delay constant defined in program example is used to illustrate the difference between constant definitions. In the left column, okay, delay is defined as 5,000 using this directive equate. Okay, while in the right, the value is stored in the memory using DW directive. So this is basically you're storing the value, but this one you're basically equating this variable with this function. So there's a bit of difference, you know. In both column, register will be loaded with this value. However, in the case we first immediate mode, while in the second case we can either use absolute or direct mode, because the here delay has a value where the datum is stored. So basically, it's just two methods of doing the same thing. But it's important for you to be able to tell the difference. Okay. Memory location can be assigned to constants using appropriate name definition. Okay, variable are names given to those labels attached to the registers. Okay, if we only separate memory, the directives in the next slide can be used. Okay, now let's look at this. Okay, so you can allocate certain memory spaces. Okay, for this for these labels. Okay, so it's very similar to this concept. Okay, where you have a label, and then you have the type, the size, and then you have the value associated to it. As I said before, it's compulsory to allocate reset vector. Okay, you also need to allocate interrupt vectors. So the CPU correspond to. If you don't allocate it, these interrupts will not work. Each peripheral I/O has an assigned address. Okay, so you can see that now each of this device you have address. Okay, in the case we are not using this model. Okay, so you need to Google up which model that you're using, and there is a reset address. Okay, but most commonly they are the same. All right, so this is you have to define the this is the reset table. Okay, so this information allow you to look at where is the reset address. Okay, it's permanently stored at this sections. The timer A reset will be stored in this section. Timer O will be stored. Watchdog timer will always be stored here. So this table is very important for you to be able to enable certain interrupts. Okay, like for example, you can have a relocatable method to. Okay, I need to get the charger because my PC running low. You give me a 1 second. Okay. So you can see that we always assign the interrupt vectors. We can have several interrupt vectors. You know, for example, this part. Okay. We assign it. Okay, this address as the reset vector, and we also have to assign if you want to use timer modules and so on and so forth. We have to assign it, and you always have this address unless you use the this method. The automated method. Else you need to define it. Where is the address and so on and so forth. If let's say anything happened, you will go to reset, etc., etc. Okay, you need to define it, and this table actually shows you where are all these interrupts. Okay, the reset address is at this point. The port 1 vector means to say that if you toggle the port 1 or whatsoever, okay, you can do something with this this interrupt. Okay, so all these interrupts in this table, this is very important for you to define. If you want to use a switch to toggle your interrupt or your LED, this is port 1 and port 2 will probably be very important for you as the I/O interrupt. Okay, so if you want to use a timer to toggle your interrupt, okay, again you need to define it just like how you define the reset. Notice that each address has a standard name which is defined in the header file. Okay, so so instead of actually naming this, at the end of when you define reset as you can write it as reset vectors. Okay, reset vectors. Okay, reset vector, not I. It's basically O. So it's FFFE. Okay, so this is the reset vector. All right. So instead of writing like this is a reserved word for reset vector. The following format is used when using the interrupt vector table. So these are all the vector table that you can use. Okay, so these are the formats. Okay, you can use ORG, 0xFFE. So this you're using the address itself. So if you want to use, let's say for example, port 1, you have to refer back to your model's address. Okay. Okay. So these are basically all the models. For me, I'm more familiar with the first method. All right. Okay. Now look at this. Similarly, look at this section. You define an interrupt, okay, and this is the reset vector. So you can write it instead of this. You can actually use this. If you include the libraries and all this, you will understand that this actually means FFFE. Okay. As a reminder, executable code is usually placed in flash ROM section of the memory space after housekeeping. Housekeeping means you clean a bit of your code so that more understandable. Interrupts are being enabled, the ENT should be introduced. Okay, so this is the part of the function. Look at it. As we said before, embedded system usually work continually. So instead of a regular stop instruction, we define infinite loops through an unconditional low power mode to terminate. Okay, this nothing associated. Now, apart from this, now we finished discussing about relocatable codes and this functions, macros. We want to look at another issue, which is the low power mode. Low power mode is extremely useful to reduce power consumption. Now, when you're designing embedded system, power is everything because the biggest inconvenience is to be able to design an embedded system. You have an Arduino or whatsoever, and if you just use a meter to tong it, you find that the ampere draw is very high. So your battery will dry off in very short time. So in order to be able to make use of low power modes, okay? So low power modes, basically they are in the status register. Still remember what's in the status register. You have your flags, your arithmetic flags, okay? And inside, together with these arithmetic flags, you have 4 bits that are actually important to define what mode you are actually going to use. Okay, so if they define it as several modes in the embedded system MSP series, they call it the low power mode 1, low power mode 2, low power mode 3. But you can actually manually assign the status register as CPU off and also ever. So if you're not using the CPU, you can actually define it to be off. Okay, so these 4 bits in the status register allows you to save power. If you're not using the CPU, you can off it. If you're not using the oscillator, you can off it, so on and so forth. When the CPU is powered up, it begins operation active mode. So this is by default. Low power modes need to be explicitly activated to take effect. So this part is actually in the book. It's only 4 bits. Only 4 bits. 4 bits will give you how many modes? 16 states. Okay, by turning on and off this few things, you can actually go into low power mode. So this is very important for people who have who are actually designing things with the this MSP. This low power mode is not something that is very specific to MSP products. You have Freescale, you have it. Microchip, you have it. All the main brands, you have this low power mode. It allows you to be able to bring something to consume power so that it doesn't draw too much. But you can actually on this by using an interrupt. So if let's say for example a user actually key in the button, okay, and from this button you can actually use the button to activate the CPU and etc. etc. Okay, so I think we've come to the conclusion for this lecture. Basically today we've only focused on a few things that you have to master. I think you're doing this for the lab also. The macros, relocatable segment, make sure you're able to differentiate between the absolute and the relocatable segment. Why is it beneficial to use relocatable segment, at least on a theoretical level? And then go and study on the low power modes. Okay, you off the CPU or whatever. What happens if I have this application? Which low power mode should I use? Okay, so that's all for today. I see you again at some other time for discussion. All right, thank you.